Okay, here's the third video for chapter 7 and 8 together. Where I kind of left off was I just introduced the fact that Schrodinger's equation is a wave-like mathematical equation that that uses as its basic foundation the fact that you can model the particles involved in a hydrogen atom using essentially wave math, the math that you would normally associate with waves, using those mathematical characteristics. Again, I'm going to try to stay away from math in these videos as much as I can. Using those characteristics, we end up using again the mathematical equation known as a partial differential equation representing a wave form. So when solving that, we ended up with some really interesting results. And the result of solving that equation, oh, I should say one more thing too, is that, and again, I'm not going to draw the equation because the equation is kind of hard to understand, but the book covers it. The equation essentially just relates energy states, essentially a possible energy states, with a particle, a charged particle traveling in an electric field. Essentially, the electric field here is the proton and the electron, and so and it measures the total energy of the system, and it takes as one of its assumptions is that energy is always conserved in the universe, as we discussed in chapter 6, I believe it was. So basically, the potential energy caused by the changing of the electric field, plus the kinetic energy of the electron, basically how fast it's moving, that value should always be constant. And anyway, that solution resulted in something fairly interesting. And it resulted in the fact that you could predict the discrete energy levels of hydrogen. Again, the ones that Bohr had also predicted in his model, and the same sort of ones that you can measure in the atomic spectrum. Those energy levels were also predicted. But it predicted that there were a certain number of them according to some quantum numbers. And again, we'd already introduced the quantum number of n, which again in Bohr's atom was kind of thought of as a level, an energy level. And so the lower values of n were at a level closer to the nucleus and were therefore lower energy, but higher values of n took the energy at higher energy states further away from the nucleus. Okay, so n was still there when you solve the Schrodinger's equation. N is one of the prime quantum numbers, and sure enough, it varies from starting at 1, and it goes all the way up from there. Schrodinger's equation also gave yielded 2 other quantum numbers as well, though, and so these 2 other ones are interesting and get us a good leap forward towards explaining some of the things we've already encountered within chemistry. So the second quantum number is known as L, and it's really kind of known as the shape. Okay, now shape. What the heck do you mean by shape? Well, so what we're kind of talking about here with these numbers that came out of the Schrodinger's equation is what came out was essentially the shape of the wave, the shape of the electron wave. Again, the base assumption here is that electron has certain wave-like characteristics. So one of the variables that are involved in the solution of this wave equation is, well, what's the shape of the wave? The level is kind of like what's the size of the wave, but the L is like what's the shape of the wave. Okay, and we'll get into shapes here soon. But anyway, that was one of the second ones, and it turns out the allowed values of L started with 0, and it goes up and ends at n minus 1. Okay, and so you can see, for example, if n is 1, the values that L can have are 0 and 0. Basically, all it can have is 0. But for an n of 2, it can have 0 and 2 minus 1, 1. So L can have 2 values for when n is 2. If n is 3, it can have 0, 1, and 3 minus 1, 2. So it can have 3 levels when n is 3, etc. So L can have different shapes, more types of shapes as n gets bigger. So as the the size of the wave, if you can use it that way, or the size of the level of the electron's movement, takes on more shapes as it gets further away from the nucleus. As it gets closer to the nucleus, it only takes on a small number of shapes. In fact, at n number equals 1, it only has one shape, period, and that turns out to be a sphere, but we'll get into that in a second. Okay, and the third quantum number that came out of the Schrodinger, solving the Schrodinger wave equation, was something called m. And this is related typically to, by the way, all of these have technical quantum names. I've left them out. You can look at those in the book. But the m quantum number refers to the orientation in space, basically in three-dimensional space. Okay. When I draw the shapes, this will be when I actually start to draw some of these shapes. M will make a bit more sense. Now, the values that m can take are essentially negative. What is it? Negative L all the way up until positive L. Okay, meaning if L is 0, then m must be 0. If L is 1, then m can be -1, 0, or +1. If L is 2, then m could take on 5 values: -2, -1, 0, +1, and +2. And it goes on from there. Okay, so basically all of these tend to take on more combinations of numbers as n gets bigger. Okay, and again, you'll see some of this as I do some of the shapes, which may be coming right next. I think here. Yeah, I think it is. So it's important to know what we're even talking about here with shapes and everything else. In fact, even going to the equation, the solution of the equation itself, the actual, other than the energy levels are one thing that you can calculate, and you can calculate discrete energy levels. But a lot of these other aspects of the equation don't even necessarily really have any kind of description in nature. And largely this is because mathematically they use imaginary numbers. They use the little I, square root of -1. Which is used in a lot of math even for things like electricity and everything else. But because of that, the trying to relate what the math is saying to you in reality sometimes doesn't make that much sense. However, when you square some of these values, and in particular if you take the absolute value of the square, in the solution of the Schrodinger equation, the absolute value of the square of something called psi actually does have a meaningful characteristic. And actually what it's referring to is that where is the position of the electron most likely to be. Now this is kind of interesting because it is showing that it isn't guaranteed to be anywhere. In fact, this is one of the spooky natures of small mass, is that when mass starts to take on some of this wave-like characteristic, it loses a lot of its classical feel, meaning that we can't relate to it very well as we relate to large things, because in a small case, for example, you can't ever really say where the electron is at any point in time. All you can basically say is where it's probably. And you can make some probability descriptions saying, well, when an energy is in a certain high energy state, when an electron is in a certain high energy state, it's most likely to be here or there, but less likely to be here or there. And that here or there is described mathematically through these equations that we're solving. And actually, these shapes and these orientations that you see are actually, you can visualize them as being shapes of a probability curve of where the electron might be. Now again, this is all kind of weird because truly at the heart of this, it says you can never tell where the electron is. And in fact, later, Heisenberg came up with a discovery that says as matter gets smaller, the uncertainty of where it is gets higher. And you can actually measure that, and there's an equation for it. It's a very famous principle called the Heisenberg uncertainty principle. That basically kind of says, you think you could always be able to say exactly where something is, because you think about that classically. But that does not become the case as objects get smaller and smaller and smaller. And in the case of an electron, in fact, as they get smaller and smaller and smaller, it takes on this wave-like characteristic as well. That's no accident, because the waves kind of behave in the same sort of spooky way. Now I'll get into the shapes. I'm going to start that in the next video, and then actually in the next video I'm going to do the shapes, and then I'm going to talk a little bit more about these numbers.